Hey, we're picking up where we left off on the last video. So fully functional. I bought some switches and just taking a look at them. They are a little smaller than the original ones. The switch part's pretty much identical. The length of them's a little shorter. You see right there. So what's really important is whether or not they fit in the holes. I know this pin spacing is a little closer together than the switches, but I couldn't find any just like that. So I'm going to see if these will be good enough to fit in there. So I'm going to go ahead and pull these two off and just stick this in there and see if it fits. And if so, then I'll probably just replace this whole row of them because I bought a bunch of them. And that way they'll be matching and we'll have a working, complete MicroMaster 8000. So I got the new switches installed. The pins didn't quite fit in there, so I did have to bend them out a little bit. So I only replaced the 3 that were missing, and I'm going to keep looking for some better ones. I probably will just dig through DigiKey or Mouser, and next time I make an order I'll get some, because what I'd really like to have is toggle switches. I think it'd be a lot easier to switch since they're so close together. So it's a few days later, and I'm not really happy with how the switches turned out, so I was looking online for what I'd really like is some little mini toggle switches, and this 150,000 spacing of the pins just isn't a standard anymore, and I'm unable to find anything. So as I showed before, I bent these pins out to make it fit, but if you look on the back of this board, these are the 8 data, well, I guess from here, the 8 data pins. You can see that, maybe you can see, the bottom 2 pins are actually tied together with a trace, and that's because this half of the switch isn't actually used. It's literally just connecting the center to the top one when you cut it on, and then it's going to open when you cut it off. So I had a thought maybe if I snipped one of the pins off that it would fit in the hole, and it does. It fits just fine. So obviously the pins are towards the inside of the holes, but don't have to bend any pins or anything. So that fits really good. So what I'm going to do is replace the 8 data lines with these switches, and that way they'll all be the same size, which just makes it a little easier to switch them, because as it is now, these original ones are a little taller, and it's easy to switch 2 at the same time. So I'm going to do that. These will be different from those, but I think that's a better solution than what I have now. So I'm going to go ahead and work on that. So I've installed the switches, and they do feel good. I was a bit worried about removing a pin of them teeter-tottering a little bit, but they're good and solid. And if we cut it on, they do all work. And they're all the same height now, so it should be a little easier to switch them without accidentally bumping another one. So in my last video I got a comment, or a couple comments, but one of the things that was mentioned is that I would hold the schematic up here to kind of show you what I was working on, and it was hard to follow because I didn't hold it up very long, and of course it's not a very good camera and stuff like that. So I think what I'd like to do is to go over the schematic a little closer, because I think this is an interesting computer. You know, I like old electronics like this. I think they're fun to work on and fun to kind of see the designs and how people did things with simpler logic. And this computer is pretty clever. You know, if you look at something like an MSI or an Altair or another S100 type computer with the front switch panels, I think that those are really cool, and I've always wanted one of those. Of course, they're very expensive, but this uses a much simpler method, and so those computers will run the processor while you're moving switches and stuff, and of course that allows you to get a little more information like current register status and stuff like that. But that ultimately what you're trying to do is program the computer, and you don't actually need the processor to program the computer. You just need to feed inputs into your RAM. So this completely allows you to do that. I think one of the negatives that makes this a little discouraging is that there's not a way to increment the address. So like on a M-SI or an Altair, you would basically hit your first address and you'd set your address with a switch, but then you would just kind of put in your data, and you'd have a switch that would do something like store it and then automatically increment to the next address. So all you're really having to do is enter data, which is a lot nicer, and this doesn't have that. I think we could come up with something to make it automatically do that, which would be pretty cool, using the expansion slot. But other than that, it is a switch computer, and I think if you're into designing simple computers, it's worth taking a look at this design, because it may be an option. Because I mean, ultimately, you just use the switches to get enough of a program in the RAM to where you can, program it or use it another way. In this case, we have a button pad and a couple 7-segment displays. So the way the manual works for this is, of course, it's a building manual. It's not really an instruction manual on using this. They don't intend you to buy it complete. They intend you to buy it as a kit and put it together. So you'd put a couple components together, and then it would kind of talk you through how it works. And then you'd put some more components in together and it'd talk you through how it works. And that's why it has a lot of these jumpers in here, because without the processor or the other parts, you have to put jumpers in to kind of trick signals to work. And of course, once everything's all together, you can use it. So I think it'd be worth going over the schematic. I think it's kind of an interesting design. When I first saw it, I saw some things that didn't really make sense, especially since a lot of it made a lot of sense. But I think I've figured it all out. I've put a post on some Facebook groups and found a guy who had an earlier version of this, and the circuitry is a little different and it makes a lot more sense. So I'll go over that as well as kind of how this thing works. So I'm just going to give a quick overview of this board, and then we'll talk about expandability, what we can do to add things to this. So start in the top left, this is just the power supply. So this S3 is where you would plug in your power, and it just goes into a 7805 linear regulator, which supplies 5 volts to the board. So everything on the board runs off of 5 volts. Up here we have our 7-segment displays. This is our keypad. This is our 8085 processor. This is the 8155 IO/RAM chip. So this is where we're getting our 256 bytes of RAM, as well as our IO ports to control the 7-segment displays and the button inputs. This 2816 device over here is the EEPROM, so that's what we actually program. That'll store memory when we cut it off and cut it back on. You can of course program either of these, but if you write anything to RAM, you'll lose it when you cut power off. So RAM's kind of, I think the way you would typically use this board with this configuration is RAM's kind of your variables for your program when it's running, and your actual programs and this 2816 EEPROM chip. So over here on the bottom left, we have some switches. Some of these are the slide switches across the bottom, and some of them are the 4. Let's see. Pull up the. So these switches as well as these 4 across the bottom, and so those are over here. This box right here represents the 8 data/address switches. And there's also a 9th one, which is right here. It's labeled as A8. So that's A0 through 7, and that's A8. And those allow us to set the data if we're writing data, or to set the address. There's an added A8 over here, which isn't next to the other ones. I'm not sure if it was an add-on or if it was originally there. But what that will do is allow you to address higher than 256. So the reason you'd want to do that is because this 2816 device is actually 2K. So that still only gives us a quarter of the addressing to write to it, but you probably don't want to write more
than that with switches anyways, but it allows you to, get more than 255 bytes written. So I imagine their monitor program is larger than that 255 bytes or 256 bytes, and that's why they have that switch on there. So right here we have these devices, which are the ones I had to replace. So this top one is let's see, 1, 2, 3 is a hex NOT gate, so it's 6 knots, and that's used as LED drivers here. They're tied directly to the address / data pins or lines, and then there's 2 NAND gates here that are just configured in a way to where they're also NOTs, and that's because they needed some NANDs over here for this circuit, so that way they could just use one chip for all of them. So the way this 8085 handles addressing is there's 16 bits of addressing, but there's only 8 bits of data because it's an 8-bit processor. So instead of having 16 pins plus 8 more, they just shared them. So address 0 through 7 is also data 0 through 7, and that's controlled through these signals over here. So this address ALE pin will go high whenever the 8085 is trying to set the address on one of the devices. RD will go low when it's telling these devices it wants to read what's in the address that it just set. This RW will go low when it's telling these devices it's writing data to them. And this IO/M is just for telling an IO chip that it's enabled, which in this IC2 it's a RAM and an IO chip, so that's the signal that lets this thing know whether it's trying to read or write to RAM or if it's trying to read or write to these IO pins up here. So when we flip this reset switch over here, which is what we do to program, the 8085 halts operation, but it also brings all of these pins over here, these signals pins, plus these address data pins to a high impedance state. So they're basically floating. So it's no longer controlling the bus, which means that we can control them through switches, which is how this board works. So you can see the switches are pulled up with 3.9 Ks. That's pretty much the values they have everywhere, and pulled down with 10 Ks. So whether you have this switch on or off, if the 8085's running, then its high and low side drivers its push-pull drivers will override those resistors. So it'll pretty much command the bus. But when we have it in a reset state, we can actually pull those pins, those buses high and low, those bus signals high and low with the switches through those resistors. And that allows us to program this without having to work with the processor at all. It just takes the processor out of the equation. So if you look at like a Altair and MSI, that's not how they work. They have a bunch of logic chips that work with the processor and simulate instructions and things like that to allow you to write to the chips. But this one just takes the processor completely out of the equation, which is kind of interesting. I wouldn't say it'd necessarily be the best idea for a production computer, of the time back then. But for a little hobby computer, it's kind of a neat way to be able to use switches to program things without having a lot of circuitry on here. And if you're into making your own little Z80 boards or whatever, this might be a pretty good technique to use. Of course, we mentioned before the kind of thing that's not user friendly about it is having to switch back and forth between entering addresses and entering data, but I think we could come up with something for that. Now this switch 5's connected to the other 2 NAND gates, and they're not really used for the board. You can see they have a jumper J3, and that jumper's not installed on my board. You would have put that on when you were building this, whenever they just had a couple components on here and they were trying to show how different things worked. In this case, it's the timer in on the 8155 that feature's not used anywhere on this board. So that allowed you to tie a switch to it, and I'm not sure what the program was, but you probably flipped the switch back and forth and counted how many times you switched it or something like that. So that was just, one of the examples, hardware examples in the build instructions, but that's not really part of how this board works. And next to the timer is this timer out, and it just goes up here to the control for which 7-segment display's on, but that jumper is also removed. In this case, in normal operation, these segments are controlled through this J12 jumper, which goes to another output on IC2, and that is the normal way of switching these back and forth. So that was another probably example in there where they cut this timer on and it just made both 7-segment displays light up with the same data, just to kind of show how that works. So that's not used either. So if we go up to the 7-segment displays and keypad, because we'll have to kind of understand that if we're going to use this thing, you can see that the 7-segment displays are all run into port B. So if you were to, for instance, bring all of these high, this would cut off because those are the cathodes of the 7-segment displays. And if you cut any of these pins on, it'll cut segments on. And if that's all we had, it would cut the segment on both of the 7-segment displays. But the anodes are controlled by this transistor circuit up here. And this is just like basically a NOT. So if you send 5 volts into this transistor, and this transistor's off, so there's nothing on the anode of this 7-segment display. So this signal is also off, and this signal being low going into this transistor cuts this one on, which will cut on this 7-segment display. So if this signal going into Q1 is high, this 7-segment display will be on. And if this signal going into Q1 is low, this 7-segment display will be on. So by toggling this pin out of the output port C0, we can switch back and forth between these two displays. So the combination of C0 and port B allows us to display different things on these displays. You just display what you want on this one, then you display what you want on that one, and just go back and forth really fast so you can't really tell. So these switches over here are multiplexed. So I'm not exactly sure how they did it, but I imagine you put voltage on one of these wires, and then you loop through and measure all of these to see if any of them are on, and then you remove voltage from there, put voltage on the next one, loop through this and see if any of them are on. And by doing that, you can see if any of these switches are pressed. So there is one more IC down here in the bottom right that I didn't talk about before. So you know how I said that data and address lines are shared? Well, that's fine for this 8155 because it uses that same method, but this 2816 doesn't do that. It has separate pins for data and for addressing, so we need a way to separate that. So this IC4 is an address latch, and what it does is you can pin this trigger 11 right here whenever the 8085 is sending an address, so it's literally just tied to the ALE line, and whatever data is on the bus at that time will get latched into this chip. And then that signal will go low, and while it's latched, it's outputting that data, which holds the address pins to the address of the bus that it was on the bus when the ALE pin was hot. So now the ALE pin's gone low and maybe data's on the bus now. Well, the address pins are still set for this device, and then they can just do a read or write whenever it's ready, and it'll supply data to the data pins that go directly onto the bus. So that's just a way to use this to separate the address and data lines so that you can use devices that don't support that. So whenever you program EEPROMs or EEPROMs, a lot of times it's really critical how long you hold the right pin low. So it's usually, nanoseconds to like a millisecond. And if you go longer than that, then you'll tend to damage the EEPROM, or your data will bleed over into other addresses. All not good things, but so Ben Eater did a video where he was manually programming an EEPROM, and he used an RC circuit to kind of crudely, make sure this write enable pin or this write signal was only pulled down or up for the correct amount of time. And but this board doesn't have that, and it seems to work just fine. So I looked up the datasheet for this device, and it actually has a built-in timer, so you can just pull it low, for as long as you want, and it'll automatically internally pull it back high whenever it's done writing. So if you did want to make something like this, it's probably worth, but it's definitely worth reading the datasheet. This is probably not the normal case. You probably typically need to control the time of that write, especially if it's an EEPROM. But if you're interested in that, I think that Ben Eater, he made a video where he basically programmed a EEPROM with switches, which is basically the exact same thing that's happening here, and he explained that very well, so I'll put that link below. The last thing to look at is the chip enable circuit down here, and that's important to understand if we're going to add any devices to this. So they are controlled off of this A15 pin, which is, you know, at the highest address pin from the microcontroller, and we don't have access to that through any of the address switches since we only go to address 8. So that's why there are, you can see there's a chip enable RAM and a chip enable ROM pin switch here. So that allows us to manually cut on those devices, because if not, you wouldn't be able to talk to this 8155 because you can't actually address that high with the switches. So if you look at A15, it goes directly into the chip enable of the ROM chip. So what that's going to do is anytime A15 is low, then the ROM chip will be enabled, which means that the ROM chip's actually enabled all the way from 0 to 32,000 whatever, and but it's only addressable through 2K. So once you get above 2047, then once you go to 2048, you'll actually be writing to address 0 of this again, which isn't really a big deal because there's nothing else on the board, just, you know, don't do it or whatever. But if we were going to add a device between here and the middle of memory, then we would need to add some circuitry externally to control that. And the way you would do that is you would remove this jumper here, so it's no longer tied directly to A15, and externally we would control this chip enable pin. So I guess I should mention, anywhere there's a little oval right here with a number beside it, that is a pin on the expansion slot. So we have access to the chip enable for this pin and also all the address lines. So we can put better logic in there to make sure that, you know, pins 15, 14, 13, 12, whatever are all low before we enable that chip, which this is missing, but it doesn't matter because there's only 2 devices. So when A15's high, it will enable this IC2. And of course, a high signal won't enable an 8155 because it needs a low signal on the chip enable. So through a bunch of switches here, it goes through this transistor here, which inverts it. And that's what really threw me off whenever I was first looking at this schematic, because we can't do the same thing that I just mentioned for enabling this IC3 externally, because we'd have to overdrive this transistor, meaning if we removed, you know, there isn't even a jumper here, which also is kind of strange, but you know, if we wanted to bring this high whenever this transistor was on, then we would be dumping all of our current through Q3, which would either break our driver or break this transistor. So it doesn't really match the rest of the board. If you look through this board, there's a lot of jumpers in a lot of places that really seem like it was well thought out to allow you to make this expandable, which I assume that they intended on either making their own expansions or people doing it themselves. But with having this transistor here, it really limits us to the lower half of memory for adding devices, and I thought that was a bit strange. Also, this transistor, let's pull up the board. If you look at this transistor, it's kind of crammed on there. In fact, you see this jumper right here that's missing? That one of the transistor pins actually shares a hole with the jumper, which doesn't really make a lot of sense. So when I was looking at the earlier board that I found on the Facebook group, it was missing that transistor. In fact, that's really the only difference. And this 8155 wasn't an 8155, it was an 8156, which has a chip enable high, which makes sense why that doesn't have a line over it. So what happened is at some point the 8155s became unavailable. They switched, the 8156 became unavailable. They switched to an 8155 and they just kind of didn't do a good job updating the schematic, and also added a circuit that kind of broke expansion capability. But so the way it originally worked is this A15 not only tied to the chip enable of the 2816, but it also tied to the chip enable of the 8155, because the 8155 will only cut on if the pin's high, and the 2816 will only cut on if it's low, so you don't actually need the transistor or anything like that. So if we want to expand this out and actually get to use that upper address space, what we need to do is, I think, without cutting traces and stuff on the board, is just put an 8156 in there, which is interesting because that's that other chip that came in the box of my kit. So if you put the 8156 in there to make it work, you just put that jumper, and of course you need to remove this transistor, and you might as well go ahead and remove these other devices. So if you remove that capacitor, that resistor, that transistor, and that resistor, and put a jumper in there, you've basically turned it into the original kit. So in order to put our own stuff externally, we need to add logic to the board to control these devices, and then just remove this jumper 1 and the jumper 2. So that's pretty cool. That seems like that's the way they intended it to work. Also, speaking of jumpers, up here there's other signals going into this processor which also go to the expansion port, which suggests that they intended on people being able to use them. Now they're tied to ground, because if these floated up, they would cause issues, because these are interrupt pins. These would make your program stop and to jump to random places in memory or whatever. So I think the intention there was to put resistors, and I say that because if you look at these jumpers right here, they're resistor spacing. I mean, at least you'd put, maybe you could put a dip switch in there. Maybe that's dip switch spacing. But the places where they have this wide spacing was either only used for when you were assembling the board and trying to learn how it worked, or there are places where it would really make sense to have a resistor. And the places where it makes sense to have a jumper, like the places you would remove and add maybe frequently if you were adding or removing expansion ports, have this 0.1 spacing, which is really convenient for just a standard jumper, like you'd find on a motherboard of a computer, or the back of an old hard drive or something for setting the address. So I think it was originally well thought out. It looks like there was just an upgrade at some point later on. Maybe a different designer added it. Maybe it was later in life and they never came out with any expansion port stuff, so they figured it didn't really matter anymore. But yeah, that circuit right there was kind of confusing me because it didn't match the design of the rest of the board. I thought the board made a lot of sense except for that. But that explains why that happened. So yeah, that's pretty much the board. You can see that anything we would want to access goes to that I/O port, that expansion port. So we could potentially, add all kinds of stuff. I think what would be neat is to just disable this 8155, the 256 bytes of memory. Just disable that altogether for RAM and only use it for I/O. So we would have to control when the I/O is enabled, through some external logic. This 2816 is an EEPROM. I mean, that's useful for having our startup code, just so that the thing will do something when you first cut it on. And I think that makes sense. It's only 2K though, and this whole, without doing paging techniques or something, this 8185 can only access 64K of memory. So I think we just probably put a 64K RAM chip on this thing. So we just have full RAM, and then make a way to switch in and out this ROM chip, and then add circuitry so that we could enable this I/O, so that we can write to the 7-segment displays and read from the buttons. And then on top of that, I mean, I think it would be cool to add the rest of the address switches, since we'll have access to full memory at that point. And also put an RS-232 port, so we could do that with just a chip. And that would basically turn it into, one of these like modern single board computers that you can buy on eBay. And that would allow us to make a little bit of ROM code so that we could read and write to the memory using the RS-232 port with some commands and stuff, and maybe make a little monitor program for a terminal. So that'd be a neat project. I think that would turn this into something really cool. Also, we have if you look at the I/O ports, port A pins 0 and 1 don't go to anything. They are left open. So we have that where we could play with. I think a neat thing to do with that would be to maybe write a program that reads and writes from a cassette tape. And so that'd be a cool way for us to store and read programs. And alternatively, with our expansion board, if we had that, we could put SPI on it, which would allow us to use an SD card. Of course, they wouldn't have had SD cards back in the day when you might have bought this kit, but it's a great, easy, simple, modern way to have a lot of storage, and that would also allow you to put programs on your computer maybe and bring them on here. But anyway, that's kind of my ideas. What would be neat for a little expansion card and how we would go about doing that. And I hope that it kind of explains how this board and this computer works a little bit.
So I think that pretty much wraps up this video. I do have an edge card connector for there, and have some nice little jumpers we can use there to make kind of the changes I was talking about before and showing the schematics for expansion. And I think that'll be kind of a fun project and turn this into something useful. So I don't know how many of these there are out there. I imagine it looks like they sold them for a long time, so I imagine there's a lot of them. I think they probably pop up on eBay from time to time. So hopefully this will be useful and it'll make something fun to do with it. When I was watching MSci Guy's videos, he was kind of saying, it's a cool thing to learn hardware, but it's not really good for software. But I think with a couple of additions, it'll be equivalent to one of the single board computers you would use to write software. So anyways, if anybody has any thoughts, suggestions, ideas, or whatever, put it in the comments below, and look forward to some future videos on this. But for now, thanks for watching.